Welcome to All in All. Today, we're setting our sights on a planet that often gets underestimated, maybe even dismissed sometimes.
Yeah, it really does.
But it truly holds some profound secrets about our solar system, and perhaps even gives us hints about planetary systems far beyond our own.
Exactly.
We're going on a deep dive into the enigmatic ice giant, Uranus.
Indeed. And Uranus is so much more than just, a distant sort of featureless orb.
Right.
This deep dive, we're going to try and uncover its unique origin story, its critical significance, why it's seen as a kind of missing link in planetary science. We'll look at its surprising impact on how we understand exoplanets, how it's evolved over cosmic timescales, and actually its very practical relevance.
Practical relevance. Interesting.
Yeah, for future space exploration and maybe even daily life here on Earth in ways you might not expect.
Okay, I'm intrigued. Get ready, because we're about to unpack some truly fascinating facts that you might not know about this faraway yet deeply significant world. Okay, let's unpack this then. Our journey into Uranus. It really begins not with a spacecraft or a probe, right? But with a telescope. And a really pivotal moment in human discovery. Unlike its well-known planetary siblings, Mars, Jupiter, Saturn, Uranus wasn't always a fixture in the night sky for us.
Not at all. For countless generations, humanity basically believed our solar system just ended definitively at Saturn.
Because that was the furthest one you could see, right? With just your eyes.
Exactly. The furthest planet bright enough to be glimpsed with the naked eye. Then boom, 1781, that long-held cosmic boundary was just shattered.
And that moment, the one that changed everything, came with the meticulous observations of William Herschel.
That's precisely right. And this wasn't just, spotting another faint star. It was a groundbreaking achievement. It fundamentally reshaped our whole astronomical understanding.
Because Uranus was the very first planet to be discovered using a telescope.
The very first. Before this, Mercury, Venus, Mars, Jupiter, Saturn, they'd been observed and tracked since ancient times, right? Visible as these sort of wandering stars. But Uranus broke that mold. It pushed the known frontiers of our solar system outwards by just an immense distance. It was really the dawn of telescopic planetary discovery.
And Herschel wasn't just some guy who, bought a telescope and pointed it up. His dedication sounds extraordinary.
Oh, completely. He meticulously crafted his own reflecting telescopes. He was grinding and polishing the mirrors himself.
Wow.
Often with the diligent and frankly equally talented assistance of his sister, Caroline Herschel.
All right, Caroline, yeah.
Their instruments became renowned for their exceptional quality. It was a real testament to their painstaking work and scientific rigor.
So this discovery, it wasn't just adding a new dot in the sky. It immediately forced this profound reevaluation of the existing models, didn't it?
Absolutely. Imagine one of those early planetary models, maybe like an intricate orrery by Benjamin Martin.
Yeah, those clockwork things.
Exactly. Initially depicting only 6 planets. Then suddenly, Uranus appears. It necessitates an immediate dramatic update. It showed right there in real time how quickly scientific knowledge can evolve.
And how even these long-held, seemingly fixed beliefs can just be overturned by new observations. A real paradigm shift.
Totally. And what's fascinating, too, is that even the name of this new world had its own little journey.
Oh, right. He didn't call it Uranus at first.
No. Initially, Herschel, maybe in a gesture of honor, maybe a bit of political savvy, he named his discovery Georgium Cetus, or George's Star, after King George III.
George's Star. Doesn't quite have the same ring to it, does it?
Not really. And as we know, that name didn't quite stick, despite his efforts.
Thankfully, yeah. It was later replaced with Uranus. Who proposed that?
That was astronomer Johann Elert Bode. He suggested aligning it with the classical mythological naming conventions used for the other planets, drawing from Greek and Roman mythology.
Which makes sense. Keeps the thing going.
And interestingly, if you look beyond just Western traditions, the idea of a celestial entity with a remarkably similar name was already kind of there in ancient cultures.
Really?
Yeah. In Sanskrit, for example, there's a celestial being called Aruna, who is the charioteer of the sun god Surya.
Aruna. Uranus. Wow, that's close.
It's a subtle but pretty striking echo across different human cultures. It sort of hints at this shared human connection to the heavens, this fascination with the sky. Even if it's just coincidence, it makes the naming story richer, I think.
Definitely. And speaking of mythology, the name Uranus itself has quite the backstory, doesn't it?
Oh, yeah, it's a big one. In Greek mythology, Uranus, or Uranos, is the primordial deity. He is the sky, basically.
Personifying the sky itself.
Exactly. He was the sun and rather awkwardly, the husband of Gaia, the Earth.
Right, that bit's always a bit much.
A little bit. Together, they fathered the first generation of Titans, creating the very fabric of the cosmos in their stories.
And then there's the famous castration by his son Cronus.
Yep, a foundational act in the mythology that led to the separation of Earth and sky, allowing the next generation of gods to emerge.
And his Roman counterpart was Caelus, right?
Caelus, correct.
Yeah.
So this planet, whether they planned it or not, has a name that's just steeped in these incredibly deep cosmic origin stories from ancient times. Kind of fitting, given its own mysterious origins. Now, if we connect this discovery to the bigger picture, Uranus isn't just, another planet wheezing around the sun.
No.
It represents a distinct and incredibly important class of celestial body, the ice giants.
Ice giants, okay.
And this classification fundamentally sets it apart from the gas giants, the big ones like Jupiter and Saturn, which are mostly hydrogen and helium.
Right.
Understanding this difference holds really vital clues about how planets form, not just here, but everywhere. They're a totally different breed of giant planet.
It's a crucial point that I think often gets glossed over. When people say giant planets, you immediately picture Jupiter, Saturn, those huge swirling gas balls. But Uranus and Neptune too, while they're still enormous compared to Earth, they are considerably smaller and have a very different internal makeup.
That's right. Just for scale, Uranus is about 14.5 Earth masses, Neptune's about 17.1, Jupiter's over 300.
Wow, okay. Big difference.
Huge difference. And Uranus is about 4 Earth radii across, Neptune's slightly smaller. So they're giants, yes, but not the same kind of behemoths as Jupiter and Saturn. And that size difference is a key clue about their composition and how they formed.
So their composition is notably different then. How so?
Well, while they probably accreted from the same basic stuff, rocks, ices, gases in the early solar system, the protosolar nebula.
Right, that big spinning disk.
Exactly. Uranus and Neptune have a much higher proportion of what astronomers call heavy elements.
Heavy meaning?
Meaning elements heavier than hydrogen and helium, things like oxygen, carbon, nitrogen, sulfur, mostly locked up in the form of various ices.
Like water ice, methane ice?
Water, methane, ammonia ices, exactly. This chemical enrichment is a key differentiator from Jupiter and Saturn, which are almost entirely hydrogen and helium. And as we'll get into later, their magnetic fields are totally bizarre, completely unlike the gas giants, which again hints at fundamental differences deep inside.
But how did Uranus actually form with this unique composition so incredibly far out in the solar system? That seems like a huge challenge.
It is. It's one of the biggest, most enduring mysteries planetary scientists are grappling with. The main model for planet formation is called core accretion.
That's the standard one, right? Build a core, then grab gas.
Pretty much. You gradually build up a solid core from dust and ice. Then its gravity gets strong enough to rapidly pull in the surrounding gas from the nebula.
Okay.
This model actually aligns pretty well with the presence of all those heavy elements, those ices we see in Uranus and Neptune. But
there's always a but.
There's always a but. It presents a major timescale challenge for distant planets like Uranus.
Too slow.
Way too slow. Forming such a large core so far from the sun, where all the building materials really sparse and the orbital periods are incredibly long, it takes a very, very long time.
Longer than the gas disk was even around.
Potentially longer than the lifespan of the protosolar nebula itself, which probably only lasted a few million years. It's trying to build a giant snowball in a blizzard that's over in minutes. Tough to do.
Okay, so core accretion has problems way out there. What else is there?
Well, there's the disk instability model. This is a different idea. It suggests a much more rapid gravitational collapse within the protoplanetary disk itself.
So the planet forms more directly from a big clump.
Kind of, yeah. A large planet forms almost directly from a gravitationally unstable clump of gas and dust. This could, theoretically, explain how you form large, distant planets quickly.
Okay, that sounds promising.
It does, but the catch is that most exoplanets we've observed, planets outside our solar system, seem to be less massive than this model typically predicts. So it might not be the universal answer, maybe just for some really big ones. Still a contender, though.
Still a contender. The challenge is finding one mechanism that explains both the fast formation and the final masses we actually see.
Okay, now here's where I remember it getting really interesting and maybe a bit wild. The migration theory.
Ah, yes, migration. This suggests Uranus, and maybe Neptune too, didn't actually form where we see them today.
You weren't born there.
Possibly not. They might have formed much closer to the sun, maybe even in the neighborhood of Jupiter or Saturn, where there was way more material available for faster growth.
Hmm.
And then through gravitational kicks and interactions with the early solar system's gas disk, or maybe other forming planets, they could have migrated outwards to their current spots.
Like being flung out.
Sort of, yeah, complex dance of gravitational interactions.
Mhm.
This theory really helps explain that timescale problem. How do you build a big planet way out there quickly? Well, maybe you don't. Maybe you build it closer in and just give it a ride outwards.
That elegantly solves the building site problem.
It does seem to help. There's also another idea, the gas capture hypothesis. Okay.
This posits that outer planets like Uranus might have captured some of their gas directly from the surrounding space or from the nebula flowing past, rather than forming strictly within a neat protoplanetary disk structure. It just highlights how messy and dynamic the early solar system probably was.
So we're left with this really critical, kind of multifaceted question then, aren't we?
We are.
How did Uranus and Neptune manage to form quickly enough before all the gas in that early disk disappeared,
Mm-hmm.
but at the same time avoid becoming even larger gas giants like Jupiter and Saturn? They stopped growing at just the right point.
Exactly. It's this delicate, almost improbable balance. It points to some very specific, maybe finely tuned conditions during their birth.
And figuring this out isn't just about Uranus, is it?
Not at all. Resolving this directly impacts our fundamental models of how planets form everywhere. It helps us interpret the incredible diversity of exoplanetary systems we're discovering now.
So if we crack the Uranus code,
We get a much better handle on how common different kinds of planetary systems might be across the entire galaxy.
okay, so the formation is a big puzzle. What about what's inside it now? You call this an ice giant.
Right, and that classification comes from its overall density being comparable to water. But here's the thing. We don't actually know for sure if water-ice material truly dominates its composition deep down.
Oh, so it might not be mostly ice.
It's possible Uranus could be more rock-dominated internally than we think. Some studies suggest that might be the case for Neptune.
Huh.
However, the presence of something highly conductive, like water perhaps mixed with other things under extreme pressure, seems strongly linked to the planet's ability to generate its bizarre magnetic field.
Through electrical conductivity, right, like a dynamo.
Exactly. But the exact amount of conductive material needed to sustain that specific weird field is still a big unknown.
Yeah.
So yeah, it's not just a simple giant ball of ice like, an ice cube. It's much more complex.
Which raises that important question about its internal structure then. Does it have distinct layers, like an onion core, mantle, atmosphere?
Mhm.
Or is it more blended? A gradual change in composition. People talk about a fuzzy core, right?
Exactly, a fuzzy core. Imagine, like you said, an avocado. Does it have that hard, distinct pit? Or does the pit sort of gradually blend into the fleshy part? That's the core debate for Uranus.
Okay.
And the problem is both theoretical simulations and lab experiments where they try to crush materials under uranium pressures and temperatures give conflicting answers.
So we can't quite replicate it yet.
It's incredibly difficult. Some results suggest materials like rock, water, and hydrogen would naturally separate into distinct layers down there. Others indicate they might remain thoroughly mixed, sort of blurring the lines between traditional planetary layers.
And finding out if it does have a fuzzy core is important. Why?
It's crucial. It would tell us a lot about its formation history, how its building blocks actually came together and mixed.
Okay.
And it would also give us vital clues about its thermal evolution, how it's cooled over billions of years, and potentially explain its surprisingly low luminosity.
Right, you mentioned it doesn't give off much internal heat compared to the other giants.
Exactly. Jupiter, Saturn, Neptune, they all radiate significantly more heat than they receive from the sun. Uranus barely does. It's strangely cold internally, or at least that heat isn't getting out efficiently.
And a fuzzy core might explain that. How?
Well, a fuzzy, less layered structure might trap heat differently, perhaps inhibiting the churning motion that would normally bring heat up from the interior to the surface. It could be the key to understanding this long-standing thermal puzzle.
Fascinating. Okay, beyond the formation and the internal structure, Uranus just presents this whole host of unique, kind of baffling characteristics, doesn't it? It sets it apart even from Neptune, its ice giant sibling.
It really does. It's a singular, often perplexing world.
And maybe the most striking feature that one everyone knows is that extreme axial tilt. 98 degrees.
98 degrees. It's effectively spinning on its side. It's almost rolling around its orbit like a cosmic bowling ball.
It's just bizarre to picture. And that leads to the most extreme seasons in the entire solar system, right?
The most extreme. Imagine one pole pointed almost directly at the sun for decades. 21 Earth years of continuous daylight, followed by 21 years of total darkness for the other pole.
Wild. And the leading theory for why it's tilted so much is
A giant impact. Scientists largely believe this violent tilt was caused by a truly gargantuan collision with something maybe Earth to Mars-sized very early in its history.
so it got knocked sideways.
Pretty much, yeah. A catastrophic impact that literally flipped it over.
And yet, despite that incredibly violent past, Uranus seems to have this comparatively calm atmosphere. You called it sluggish.
Yeah, sluggish is a good word for it sometimes. It shows far fewer visible storms, cloud bands, and big weather events compared to Neptune, which is often this swirling canvas of activity with dark spots and bright clouds.
Neptune looks much more dynamic. Uranus often just looks blue-green.
Exactly. Often calm, almost featureless from a distance. And this atmospheric quietness might be a direct result of that negligible internal heat source we just talked about.
Ah, less heat bubbling up from inside means less churning in the atmosphere.
Precisely. If there's less internal heat driving convection and atmospheric dynamics, you'd expect a less active, more stable-looking atmosphere.
And that lack of heat could be linked back to the impact, maybe. Did it vent all its heat?
That's one possibility. Maybe the impact released a huge amount of its primordial heat early on, or alternatively, maybe energy is trapped deep inside by stable layers, preventing it from getting to the surface efficiently. It connects back to that internal structure question again.
It all seems interconnected.
Very much so.
But our knowledge of the atmosphere is still pretty limited then, because it is so quiet.
Frustratingly limited, yes. The visible cloud features are thought to be mostly methane ice crystals, which give it that blue-green color by absorbing red light, and possibly hydrogen sulfide ices deeper down, which would give it a pretty pungent rotten egg smell if you could somehow get close enough.
Lovely.
Charming, right. But we lack a really well-constrained wind profile, especially deeper down because there are so few easily trackable cloud features. Even Voyager 2's flyby was just a snapshot.
So you can't easily see how fast things are moving.
Exactly. When storms do pop up, they tend to appear suddenly, get sheared apart by the winds we can infer, and then dissipate quickly. We don't really know how deep they go or what drives them. We just don't have enough persistent, well-defined features to map the circulation properly.
Which is why future missions are so critical for this.
Absolutely. They're designed to study variations in temperature, composition, and aerosols across different latitudes in much greater detail.
And use techniques like radio occultation. What's that?
That's where a radio signal from the orbiting spacecraft passes through the atmosphere just before or after it goes behind the planet from Earth's perspective. By analyzing how that signal changes as it passes through the atmosphere, scientists can detect subtle vertical structures, measure temperature and pressure profiles very accurately, and even potentially detect lightning flashes. It gives us a way to probe the atmosphere vertically, not just horizontally.
Getting a much clearer, deeper picture. Okay. And then there's Uranus's magnetic field. You said it was wild.
Oh, it's truly wild. It's entirely unlike any other in our solar system, maybe unique in the known universe, honestly.
What's so weird about it?
Well, its magnetic dipole axis, think of the main north-south line of the magnet, is wildly offset by a staggering 59 degrees from its rotational axis.
59 degrees. So if the planet spins like this, gestures upright spin.
Yeah.
The magnet points almost sideways.
Exactly. Imagine a spinning top, but the big bar magnet inside it is tilted almost 60 degrees off kilter.
Okay, that's weird.
And it gets weirder. The magnetic center isn't even at the planet's geometric center. It's significantly offset from the middle, too.
So it's tilted and off-center.
Tilted and off-center. And this combination generates these highly unusual, lopsided, and time-variable interactions with the solar wind, that stream of charged particles blowing out from the sun.
Must be chaotic.
It seems to be. The brief Voyager 2 flyby in '86 only gave us this tantalizing snapshot, just one moment in time.
What did it show?
It showed a magnetosphere, the magnetic bubble around the planet where rotational effects, which totally dominate at Jupiter and create its powerful organized field,
Right.
and solar wind-driven convection, which is more like how Earth's magnetosphere works,
Right, yeah.
were happening simultaneously. It was this bizarre hybrid, a unique configuration that scientists are still really struggling to fully model and understand.
We have longer-term data now, too.
We do, from Earth-based observations and spacecraft monitoring the solar wind itself. And what's fascinating is that this data indicates a slow but significant decline in the solar wind's outward pressure since around 1990.
Okay, the solar wind got weaker.
Effectively, yeah. And this decline strikingly mirrors a decline observed in Uranus's thermosphere temperature over the same period.
Its upper atmosphere got cooler as the solar wind weakened?
Exactly. This strong correlation suggests that Uranus's upper atmosphere temperature isn't primarily controlled by sunlight like Earth's is. Instead, it seems to be controlled by the solar wind pressure puffing up or shrinking its magnetic bubble.
So the magnetosphere size directly affects the upper atmosphere temperature.
That seems to be the implication. It's a much more direct dynamic interaction between Uranus's unique magnetic field and its space environment than we see elsewhere. Profoundly different.
And what happens around equinox? You mentioned that earlier.
Right. So because of that extreme 98-degree tilt around equinox, the sun is shining directly over Uranus's equator. Models suggest that during this time, the magnetosphere becomes particularly dynamic and variable.
How so?
Processes like the Dungy cycle, that's where the planet's internal magnetic field lines break and reconnect with the magnetic field lines carried by the solar wind.
Allowing solar wind energy in.
Exactly. That process might be turning on and off multiple times within Uranus's short 17.3-hour rotation period during equinox.
So the whole magnetosphere could be rapidly reconfiguring itself constantly.
Could be, yeah. Creating this really chaotic, rapidly changing magnetic environment, very different from Earth's relatively stable field.
Incredible complexity. But it all comes back to that fundamental puzzle, doesn't it? Tying back to the fuzzy core idea. What kind of dynamo process inside Uranus actually produces this incredibly complex, off-kilter variable magnetic field?
That's the million-dollar question, or maybe billion-dollar given mission costs.
Yeah.
Is it generated in a thin, electrically conducting shell, maybe salty water near the surface? Or does it come from deeper within, throughout a convective, fuzzy interior? We don't know.
Well, we can't even be sure of the planet's true rotation rate.
Not precisely. The magnetic field itself generates powerful radio signals, but because the field is so complex and offset, those signals can actually obscure the underlying rotation rate of the planet's deep interior. It makes it surprisingly difficult to nail down its exact day length.
Wow. So many deep, interconnected questions about just how this planet works.
Absolutely. And the mysteries extend to its family too, its moons and rings.
Right. Unlike Neptune's big moon Triton, which we think was captured.
Exactly. Triton is widely believed to be a captured Kuiper Belt object, basically a dwarf planet like Pluto that wandered too close and got caught in Neptune's gravity.
But Uranus's moons are different.
Yes. Uranus possesses a natural primordial satellite system. This suggests a very different formation story for its moons. They likely formed from a disk of gas and dust swirling around Uranus itself, much like the planets formed around the sun, just on a smaller scale.
Like a mini solar system.
Pretty much. And within that system, Titania, one of Uranus's largest moons, is particularly interesting.
Why Titania specifically?
Because it's large enough and potentially has the right composition that it could possibly sustain a present-day subsurface ocean.
Liquid water under the ice. Like Europa or Enceladus.
Potentially, yes. Like several other large icy moons in the outer solar system, Titania might retain enough internal heat, maybe from radioactive decay in its core, or from tidal forces due to Uranus's gravity, to keep a layer of water liquid beneath its icy crust.
Which makes it a prime target for astrobiology. Looking for life.
It definitely makes it a target for future exploration. Finding liquid water, a key ingredient for life as we know it, in such an unexpected, distant place would be incredible.
Absolutely. And Uranus has rings too, right? Fainter than Saturn's, but there.
It does, a complex system of narrow, dark rings. And though they're faint, they offer this unique and incredibly powerful opportunity for something called ring seismology.
Ring seismology. Using the rings to study the planet.
Exactly. Think of the rings as a colossal natural seismograph spread out in space around the planet.
Okay. How does that work?
By precisely measuring how the particles within the rings respond to Uranus's gravitational pull, how they wobble, how specific waves or patterns propagate through them, how their orbits subtly change over time. Scientists can effectively listen to the planet's interior. These gravitational ripples reveal subtle details about Uranus's internal structure changes in density, the distribution of mass, maybe even the presence or absence of that fuzzy core things that are otherwise totally invisible from the outside.
Wow. So the rings act like a probe of the deep interior.
In a way, yes. It's a technique that's been used successfully at Saturn with Cassini, and Uranus offers an equally rich, maybe even more complex laboratory for it because its ring system is quite different from Saturn's.
Okay, this is where it gets really, really interesting for me, how Uranus connects beyond just itself. It's not just this isolated oddball out there.
Not at all.
It actually plays this surprisingly profound role in helping us understand planets way beyond our solar system and maybe even impacts how we see ourselves.
That's absolutely right. Uranus serves as, you could say, an ideal target and a crucial proxy for scientists practicing how to analyze and understand exoplanets.
Planets orbiting other stars. Why Uranus specifically?
Because many of the exoplanets we're detecting fall into this category of sub-Neptunes, or ice giants. They're similar in size and likely nature to Uranus and Neptune. They seem to be a very common type of planet out there in the galaxy.
So studying Uranus up close gives us a blueprint.
Exactly. It lets us hone our observation techniques, figure out what the spectroscopic signatures of an ice giant atmosphere actually look like, develop better models for their insides.
Sure.
All of which we can then apply to interpreting those incredibly faint, distant signals we get from exoplanets. It's like having a fantastic, relatively nearby lab sample to practice on before we tackle the really hard, distant cases.
And didn't Hubble and New Horizons do something like this recently? Observe Uranus together.
They did. It was a brilliant piece of coordinated observation. NASA's Hubble Space Telescope and the New Horizons spacecraft looked at Uranus simultaneously, but from vastly different viewpoints.
New Horizons being way out past Pluto by then, right?
Exactly. New Horizons was about 6.5 billion miles from Earth and 4 billion miles from Uranus at the time. From that immense distance, it saw Uranus as just a few pixels across, a tiny, unresolved blue dot.
Just like how we see distant exoplanets now with telescopes like Webb.
Precisely. It was a perfect simulation of observing a distant exoplanet.
And Hubble, closer in.
Hubble, orbiting Earth, only about 1.7 billion miles from Uranus, provided the high-resolution context. It could actually see details, clouds, storms, hazes on Uranus's day side, features that New Horizons simply couldn't resolve.
So you get the distant blurry view and the close-up detailed view at the same time.
Exactly. And comparing those helps scientists understand what features can be discerned at different resolutions, what subtle signals in the blurry view might correspond to real weather patterns seen in the detailed view. It gives them invaluable practice in decoding those tiny points of light from alien worlds. A fantastic calibration exercise.
That's really clever.
Okay.
Connecting this to the bigger picture within our own solar system now, Uranus's influence stretches even further, doesn't it? Affecting Jupiter.
It does. It's definitely not an isolated system out there. Our solar system is this incredibly complex, delicately choreographed ballet of gravitational forces.
Everything pulls on everything else.
Pretty much. And subtle variations in Uranus's orbit over very long timescales, millions of years, are believed to actually drive the precession, the slow wobble of Jupiter's spin axis.
Wow. Uranus makes Jupiter wobble.
It contributes significantly, yes. This seemingly distant connection just reveals how profound and far-reaching the gravitational influence of these massive outer planets is on the entire system. They're all locked in this intricate gravitational web.
Which raises a really important, maybe even slightly sobering question about Earth's stability, doesn't it?
It does.
We often hear Jupiter, with its huge mass, is essential for us. It acts like a cosmic bodyguard, right?
Yeah.
Protecting us from asteroid and comet impacts.
That's the common understanding, yes. Its gravity helps clear out potentially hazardous objects or deflect them.
But this cosmic protection relies on a really delicate balance, doesn't it?
It seems so. Without the precise, finely tuned properties and orbital configurations of all these gas and ice giants, their collective gravitational pull could actually disrupt Earth's orbit over millions of years.
Yeah.
It could potentially nudge us too close to the sun or too far away, making our planet uninhabitable. The very stability we depend on seems to point to this complex, integrated solar system design, where each planet plays a crucial, interconnected role in the stability of all the others, including our own fragile existence. It's a remarkable piece of cosmic architecture.
It really makes you appreciate the whole system. Now, moving beyond pure astronomy, Uranus also holds this cultural significance, right? Particularly in astrology.
It does. In astrology, it's often seen as the planet of rebellion, innovation, sudden change, and societal growth. It's linked to breakthroughs, independence, technology.
And even things like cosmic love and altruism, I read.
Yeah, those interpretations are out there too. It's a fascinating example of how humans have historically tried to map celestial movements onto our own experiences and the patterns we see in society.
And astrologically, its position as it moved through the zodiac signs over decades is set to define whole generations.
That's the idea. Astrologers look at the sign Uranus was in when a generation was born to understand their collective character or challenges. For instance, for the baby boomers, Uranus moved through Gemini, Cancer, Leo, and Virgo, roughly between 1942 and 1969.
And what's the interpretation there?
Well, it's often linked to learning how to protest, assert power, use their voice for change, Gemini, protect community, Cancer, express themselves creatively and politically, Leo, and develop a critical eye towards injustice, Virgo. It provides this framework for looking at the identity of that generation.
Interesting. What about Generation X, born roughly 69 to 88? Uranus was in Virgo, Libra, Scorpio then.
Right. For Gen X, the astrological interpretation often focuses on forging their own identities in relationships, questioning norms, Libra, dealing with transformation and intensity, Scorpio. This period included the societal shock of the AIDS epidemic, and Uranus and Scorpio sometimes linked to that acute awareness around safe sex, intimacy, and public health crises, reflecting maybe a more challenging independent path.
Okay. But what about the youngest generation, Generation Alpha, born roughly 2010 to 2024? Uranus has been moving through Aries and now Taurus.
For Gen Alpha, the astrological links being made now often relate to investing energy in tackling the climate crisis, Taurus relating to Earth and resources, exploring new financial systems like crypto, Taurus and value, and maybe a focus on self-care, personal values, and even beauty projects.
It's definitely interesting to see how these broad societal trends get mapped onto these slow planetary cycles. A different lens on history, I suppose.
It is. Now, bringing it back to the science, all these unanswered questions we've discussed, the formation, the interior, the tilt, the magnetic field, the atmosphere, the moons.
Yeah, there's a lot.
There is a lot. It all leads to one really undeniable conclusion. We absolutely need to go back.
To Uranus.
To Uranus. Despite their huge scientific potential, Uranus and Neptune are still the only class of planet in our solar system we haven't studied intensively with an orbiter. Voyager 2 was amazing, but it was just a flyby.
Less than a day of close-up science, you said.
Less than a day. It barely scratched the surface. This leaves this vast, unexplored frontier, just packed with data that could absolutely revolutionize our understanding of planetary science.
The scientific imperative seems clear.
Yeah.
But the challenges are huge too, right? It's just so far away.
Immense challenges. Solar panels are basically useless out there. The sunlight is way too faint.
So missions need nuclear power sources, RTGs.
Exactly. Radioisotope thermoelectric generators, they produce electricity from the heat of decaying plutonium. They're reliable, but they're heavy, and provide limited power compared to solar panels closer in. That constrains what instruments you can run and for how long.
And just getting there takes a lot of energy, a lot of fuel.
A huge amount of delta V, yes, the change in velocity needed. That often pushes mission planners towards closer, easier targets like Jupiter or Saturn, where you need less fuel for the journey and especially for slowing down to get into orbit. Sending a big orbiter to Uranus requires overcoming some formidable technical and financial hurdles.
But despite those hurdles, the scientific community is really pushing for it now.
Harder than ever. NASA's latest Planetary Science Decadal Survey, which is basically the science community's consensus wish list and roadmap for the next 10 years, identified a Uranus mission as the absolute #1 top priority for the next big flagship mission.
Wow, #1 priority. That's huge.
It's a monumental endorsement. It puts Uranus right at the forefront of future deep space exploration plans.
And the proposed mission is called the Uranus Orbiter and Probe. UOP.
That's the concept, yes. An orbiter to study the planet, its rings and moons over several years, plus an atmospheric probe to plunge directly into the atmosphere and measure its composition.
Ambitious. What's the rough cost?
Estimated around $4.2 billion total, maybe $2.8 billion just for the spacecraft and instruments, not including the powerful launch vehicle needed. That's comparable in scale and cost to other big flagship missions like Cassini at Saturn or the Europa Clipper heading to Jupiter.
So a major investment, but deemed essential.
Absolutely essential for making the next big leap in planetary science.
And when could this potentially launch? And how long would it take to get there?
The earliest realistic launch window they're looking at is around 2031 or 2032. And then, yeah, it's a long cruise, about 13 years to reach Uranus.
13 years. Just coasting through space.
A long haul. And a key driver for that timeline is aiming to arrive before the 2050 equinox at Uranus.
To see the magnetosphere during that dynamic period you mentioned.
Exactly. Arriving before then would let the mission observe Uranus in that unique solar wind orientation, giving us invaluable data on how that bizarre magnetosphere behaves under conditions we've never seen up close.
Okay, so technologically, how do you make a 13-year journey with a heavy spacecraft feasible?
Well, using Jupiter's gravity is key. A Jupiter Gravity Assist, or JGA.
The slingshot maneuver.
The classic slingshot. It's crucial for both saving fuel, making the mission cheaper, and significantly shortening the travel time. A well-timed JGA can potentially provide 40% to 90% more launch mass capability, meaning you can send a bigger, more capable spacecraft for the same launch costs.
Makes sense. What about slowing down when you get there? That takes a lot of fuel, too.
It does, and that's where another really innovative, though challenging technology comes in, aerocapture.
Aerocapture, using the atmosphere to brake.
Exactly. Instead of firing powerful rockets for a long, fuel-guzzling burn to slow down and enter orbit, the spacecraft would essentially skim the upper layers of Uranus's atmosphere.
Wow, like hitting the brakes using air resistance?
Pretty much, yeah. Atmospheric friction would shed tremendous velocity. It could potentially reduce the amount of propellant needed for orbit insertion by 60 or 70%.
That's huge.
It's enormous. And it could also cut the total cruise time by several years because you don't need to arrive quite as slowly. It's high stakes, technically very difficult, but the payoff for deep space missions is potentially massive. It could make previously impossible missions feasible.
Very cool. And they're also thinking about how to deploy the atmospheric probe safely.
Yes, a key risk reduction strategy is to not deploy the probe while the spacecraft is still hurtling towards the planet on approach.
Why not?
Because the entry speed would be incredibly high. Instead, the plan is for the main orbiter to carry the probe through the orbit insertion maneuver first, get the orbiter safely captured into a stable orbit around Uranus, and then release the probe. This allows the probe to enter the atmosphere at a much lower velocity, which reduces the intense heat and stress it experiences. Plus, it provides backup opportunities if the first orbit insertion attempt has issues. It makes the whole mission much more robust.
Smart thinking. So, what are the main science goals for this UOP mission? What do we hope to learn?
Oh, the goals are incredibly ambitious and transformative. A big one is direct measurements of noble gas abundances, helium, neon, argon, krypton, xenon, and their isotopes deep in the atmosphere with the probe.
Why are noble gases so important?
Because they're chemically inert, they basically preserve a fingerprint of the original protosolar nebula material from which the planets formed. Measuring them precisely tells us about the raw ingredients of the solar system and the conditions during planet formation. It's fundamental stuff.
Okay, what else?
The orbiter will map Uranus's gravity field with incredible accuracy, down to tiny variations.
To figure out the internal structure, fuzzy core or layers.
Exactly. The gravity map will reveal the bulk composition, how density changes with depth, and should definitively tell us if it has those distinct layers or a more gradual fuzzy core.
Finally answer that quite fast.
It also aims to pin down Uranus's true rotation rate, measure the depth of its atmospheric winds, study that complex magnetic field and its interaction with the solar wind in unprecedented detail, and, of course, investigate the potential for subsurface ocean worlds within its moon system, especially looking closely at Titania for signs of geological activity or plumes that might hint at liquid water.
Exploring its astrobiological potential, too. It sounds like a comprehensive, really generation-defining exploration mission.
It absolutely is. It would fill a huge gap in our knowledge.
And this relentless push for cosmic exploration, it isn't just about satisfying curiosity about distant worlds, is it? Astronomy seems to constantly drive innovation that benefits us right back here on Earth.
In profound, often unseen ways. It's easy to think of space exploration as this separate, expensive thing, but the connections to our daily lives are absolutely everywhere, woven into the fabric of modern society.
Like what kind of technologies?
Well, many we use every single day are direct legacies. The computers we're using right now, the satellites enabling global communication and weather forecasting.
Right.
Smartphones rely heavily on GPS technology, which was derived directly from software developed at NASA's Jet Propulsion Lab for precisely positioning spacecraft across the solar system.
Wow, didn't know the direct GPS link.
Yeah. And things like energy-efficient solar panels, advanced digital camera sensors, the CCD and CMOS sensors in everything from professional cameras down to your phone, airport security scanners, portable X-ray machines in hospitals, even MRI scanners. They originated from nuclear magnetic resonance research, a technique astronomers developed and used to study cosmic magnetic fields and molecules in space.
MRI scanners came from astronomy. That's incredible.
The fundamental physics and early techniques, yeah. The applications spread far and wide.
And what about software?
The highly specialized software developed for astronomers to handle and analyze just colossal amounts of data. Think about mapping billions of stars or finding tiny dips in light from exoplanets.
Yeah, huge data sets.
That software, those algorithms, are often repurposed and adapted across countless other industries. Financial modeling, complex data analysis, medical imaging analysis, environmental monitoring. The tools built for looking out often end up helping us look inward or around us.
So the same code analyzing galaxies might help a doctor analyze a patient's scan.
It's entirely possible, yes. The underlying mathematical and computational techniques are often transferable.
And just studying other planets, does that help us understand Earth better too?
Absolutely, in a fundamental way. By studying other planets, we get comparative planetology. We see how geology works under different gravity, how atmospheres evolve under different conditions, how magnetic fields protect planets or don't. It helps us refine our understanding of Earth's own geological processes, its atmospheric evolution, its climate history, its deep past. Observing how other worlds formed and changed gives us invaluable perspective on the processes that shaped and continue to shape our home.
It gives context to our own world.
Precisely. And ultimately, I think the impulse to explore the cosmos, it really unites humanity. It cuts across cultures and disciplines. It fosters ingenuity, pushes the boundaries of engineering and science, and maybe most importantly, it gives us that broader perspective on our own unique, fragile place in the universe.
It's an investment in curiosity that seems to consistently pay off in unexpected ways.
Always. Pushing the boundaries of knowledge always yields unexpected treasures.
What an incredible deep dive into Uranus this has been.
Yeah.
Seriously. From its humble beginnings as the first planet spotted through a telescope to its incredibly complex and puzzling interior, that bizarre magnetic field, its strange tilt. And now, understanding its role as this crucial stepping stone for unlocking exoplanet mysteries and even driving technological progress right here on Earth.
It really does highlight how deeply intertwined our exploration of the cosmos is with our progress right here on Earth and our understanding of fundamental physics.
Yeah.
The mysteries still surrounding Uranus are just this powerful reminder that sometimes venturing further out into the most distant and maybe seemingly obscure corners of our own solar system is exactly where we find the most profound insights that come back home, shaping our present and our future.
That's beautifully put. And for you listening, as you consider the incredible scope of this deep dive, maybe the next time you look up at the night sky, you probably won't see Uranus without a good telescope.
True.
But maybe you'll think of it differently. Not just as a distant point of light or, the butt of jokes.
Hopefully not.
Hopefully not anymore. But as this silent, spinning, sideways laboratory out there, holding truly universal secrets, just waiting for us to unlock them. And it makes you wonder, doesn't it? What other seemingly obscure areas of knowledge, maybe things we overlook today, might hold unexpected keys to our future, if only we dared to look a little closer?
A great question to ponder.
Thanks for listening to All and All.